I'm very happy to be in this workshop. Thank you for the invitation. So, as you said, I'm working now in a small company called Montimage. We are located in Paris, and we are experts in cybersecurity. And we have several security solutions that we are building and innovating, and we are part in several European projects and also local projects, local innovation projects. So in this workshop, we are trying to link network AI and cybersecurity. We saw how we can use AI to somehow automate the management of networks, how to use AI to enhance cybersecurity solution, enhance management of the security in networks. But we need also to know that this AI can be used also by attackers to enhance the quality of attacks that they can generate. Of course, they can also be used by, let's say, legitimate red team in a company to perform also some penetration testing to assess that the target system or network that they are using is somehow secure enough, resilient enough to attacks. And to be able that, they need to have tools to be to discover these vulnerabilities on the target system, to exploit these vulnerabilities. And there is a lot of techniques that allow to do this kind of penetration testing. It can be risk-based testing, database testing, data related testing, model-based testing, but we can also have some solution based on fuzzing, and this is what we'll do, and we'll see today how fuzzing can be one of the techniques finally to assess the security of a target network, and how AI can enhance also this fuzzing. I guess that you know already what is network fuzzing. So the idea is to use the security testing technique to send malformed unexpected packet to a target system. So the idea is to be able to generate this malformed and this, let's say, unexpected flow. And then the idea is to check how the target system will react to these packets. It may cause some crashes, some memory leaks, we can detect vulnerabilities. And the idea, of course, when we do that is then to discover these issues and try to recover them, to apply some remediations to do and correct the behavior of your network. There is in general several steps. Of course, the input will be some network packets from the target system. It can be a pre-captured network packets, so it can be some pickup files that we have already captured from the system. That can be a complex system with the different, let's say, services, protocols, and even in terms of complexity of sub-networks, etc. And we can also do it in an online way by finally connecting to a network interface or to tap mirroring and to gather this network online and to automatically change it and forge new packets that can be malicious packets that can harm the security of the target system. When I say generate new packets, that means that we are doing somehow some mutation of this nominal traffic, and we need to define some mutation functions, what kind of mutation we can do on these packets. Should we delete some packets, duplicate some others, maybe change the field, different fields values in some protocols. We can also change the order of packets. We can do a lot of things. So depending on these functions, and of course we'll inject these mutated packets. We'll monitor the response of the system. We can see it from the network point of view, but we can also monitor the system logs, the services logs, the application logs, even the hardware if needed part, and all these finally analysis will allow us to assess the robustness of the target system, identify the weaknesses, and of course, the idea is also to propose corrective actions to build a better, reliable network. Now, with AI, the idea is not to rely only on some rule-based mutation systems or random mutations to apply anything randomly, but to have some intelligence in this generation of attacks, and AI, enhanced fuzzer, can bring this improvement into network fuzzers by finally taking into account the feedback loop from the target system to take it as an input in our generations. So, for example, if I know that this kind of mutation will not have any impact on the system, I will not generate packets from the same way for this specific mutation. We know that they are not very impactful. So the idea is to finally have more information that and this feedback loop that will allow us to guide this generation of attacks. We can also rely on several, let's say, algorithms. One of them can be the GAN, generative adversarial networks, to generate realistic and malicious traffic. I don't know if you know the GAN. I guess yes. With these two networks, one to generate and a network for discriminator to select the one that are, let's say, more interesting for us. We can also use LLMs to generate some rules automatically and not write them manually. So the modification will not be done by a human. The modification rules and mutation can be also generated based, of course, on some known risk or known issues that we can have and from a risk assessment, or even from RFCs of some protocols. We know already that they have this kind of vulnerability. So why not, from this information, we can generate automatically some modification on the network that will mimic finally some known attacks. So finally, this usage of AI will somehow bring this intelligence to network fuzzer. And this is what we are trying to do in Montimage, because Montimage, we since many years now, we have this expertise on cybersecurity almost from 20 years ago, where we started using classical tools to do some generation of attacks using, of course, classical tools like now maybe some of you know the tools proposed by Kali Linux or Parrot system. We are also using some TCP replay to replay some traffic and also mutated. We are using some Python library like Scapy that also to work on the let's say different fields and change them and generate and forge new packets. So this is classical way. Then we noticed that this kind of tools cannot be applicable, for example, to new protocols or particular protocols. We had some project that dealt with the 5G security. So with the core of 5G, where we are using new kind of protocols, and TCP replay is not able to decode this protocol and allow to finally to do some modification. So we created an open source tool called 5G Replay that is an open source solution that you can find on GitHub. It has been built in the context of two European projects, Sancus and Inspire 5G Plus. And now this tool is used by a lot of people that are dealing with 5G. We are seeing in Europe a lot of people, including this kind of solution in their test beds or in their cyber range to allow to generate different kind of attacks. These tools is somehow based on some rule-based modification that will specify somehow how some attacks that are targeting some specific protocol in 5G can work, and we can generate this kind of attacks, and have also the possibility to do some random generation of 5G traffic that can be malicious or not, depending on this randomness that we use. And starting from 2025, even before, because we started before, in the context of some project that we have, one of them is AI for cyber. So applying AI to cybersecurity. So in this project, we have a lot of cybersecurity solutions, but we have also solution for pen testing. So we are using AI for risk, AI for intrusion detection, AI for SOAR, AI for honeypots, AI for collaboration and information sharing, etc. So we are using this AI for code, also for secure coding, secure fixing. And we have this AI to generate attacks. So we created a tool called AI for SIM to simulate attacks. And in this tool, there is 7 tools or sub-tools, because the techniques to generate attacks are different. Some of them are LLM-based, other are model-based, etc., etc. And one of them is this AI Fuzzer that is proposed by Montimage, and we are continuing working on that in another project called Intact. The idea is not only to target 5G protocols like 5G replay, but to have diverse protocols, and also to use advanced AI techniques. So for 5G replay itself, as you can see, we have as an input some pickup file or some NIC interfaces, and the packets will arrive. We have a default, let's say, management of these packets. Either they are, let's say, one of the modification rules is applicable. So in this case, we'll do the modification that is specified in the rule, or we do the, let's say, the default way of managing this packet, either forward it as it is or drop it, okay? And the modification itself is a contextual modification. So if I am in a specific context, I will do this specific modification, or this one, or this one. And we have some mutation operators related to some deletion of packets, duplication of packets, modification of some packet fields, reordering of packets. We can also work on session level and not packet level to also duplicate sessions or delete sessions, etc. We can also work on the bit rate to have, let's say, more packets per second, or more or less, depends on what we need to do as mutation. And of course, we can combine all of them, and we can work on a lot of packets at the same time, because we need also to take into account this logic of a protocol where there is this communication and the logic of this communication. The problem, or let's say the challenges, because the tool works good, but we can, first of all, we need to write, if it's not a random modification, we need to write manually some modification that will somehow describe some specific attacks. Sometimes we have also this lack of context awareness, because we are not somehow checking how the target system is reacting. So we don't know if what we are doing is really interesting or not. And of course, we have this lack of this intelligence if you do any random, let's say, generation. That's why we wanted to have something more sophisticated, and we have this new architecture of this smart network fuzzer, where first of all, we would like to use LLMs to be able to generate some modification rules. So this is something interesting, to not write modification rules manually. Of course, we have our own way of writing these modification rules using some XML, but we have also some mutation function that we implemented ourselves. but we can rely on some description of attacks that are targeting a specific system. We can rely on some framework like Mitre attack that describe a lot of attacks, and based on this, let's say, not let's say the description in natural language, we can maybe generate some modification rule automatically using LLMs. And we can also do some prompt engineering to say, I would like to have a modification rule that do that, and describe what kind of modification. And automatically I can be able to have the modification rule automatically that will help the person that is writing this rule. In terms of generation of attacks, the first part in blue is built on some reinforcement learning, in the sense that the packet that we are modifying and finally sending to the target system, so the blue part is the target system, we are collecting some metrics on network, on system, on application, to check what is happening in target system. We are using, in fact, our monitoring tool called MMT, Montimage Monitoring Tool, to collect this information and to give finally this feedback, so based on the reinforcement learning, to our system to finally select the rules that that are the more impactful on the target system. Okay, so these rules can be somehow launched during a testing phase in priority. And we are also investigating the usage of GAN, in the sense that we are applying some known libraries, maybe no CTGAN, but CTGAN works only on CSV, not on packets. So the idea is to transform the pickups to CSV based on some tools like flow meters, or even our Montimage monitoring tool can also transform pickups to some reporting CSV. And then using CTGAN, we are able to generate new CSVs with the new information. And from these CSVs, we can generate the packet again and launch it to the system. Okay. Of course, in the CTGAN, there is this discriminator that allows to select the best CSVs that are relevant for a specific context. So we are building this, let's say, solution that is also available on GitHub. We are also improving it. So we will see that it's a work on progress. We are always, let's say, improving the solution. And we applied this to several contexts. Of course, 5G was one of the contexts. And in the context of AI for cyber, we have, in fact, 3 pilots, one linked to energy, one linked to banking, and the third one is linked to e-health. So here, this is the case of e-health, where we have this PAX server. PAX is a server where we can store and transmit and share medical images between devices, and of course radiologists that can read these images from any patient. It relies on a protocol called DICOM. DICOM stands for Digital Imaging and Communication in Medicine. And the idea, of course, you can imagine if you are performing a kind of man-in-the-middle attack, and we are able to connect to this communication, DICOM communication with this PAX server, we will be able then to inject some malicious, let's say, packet to this PAX server, either to access to some private information, that can be a privacy issue, if you access to images of some patient, and so you can know what they are having as disease or whatever, or we can even alter this information and these images, and of course, later on, maybe the diagnostic will be incorrect from the radiologist. And this kind of mutation can be done with our network fuzzer, and this is what we did in the context of AI for cyber, and in the context of this Portuguese hospital called HES. So of course we need, first of all, to be able to decode the DICOM protocol. We have in this network fuzzer rely on a module that has a plugin architecture to be able to add new protocols or even proprietary protocols. This same module is used in our monitoring solution. So it's modular solution. So we take it as it is. The idea is to be able to decode. And then, of course, for an intrusion detection system, it will apply some detection rules. And for fuzzer, it will modify the packets and send the new packets. So, but the first step to be able to capture and decode has the same thing. So we have already more than 600 protocols that are supported, and we added this DICOM protocol to have some what we call attributes. They are in general fields value, but in fields if the information is a raw information, but we call it attribute because we can also do some computation to have some averages. We can have some metadata on the packets, etc. So that's why we are using the word feature or attribute in this case. So we collect several attributes, and we are able already to write I think 34 rules that describe known attacks in DICOM. But the idea is not only to have known attacks, but also to generate things that we don't know, not randomly, but in a smart way. And that's why we use this GAN-based traffic generator that will extract the information from the packets, will train the city GAN, will also generate synthetic flows that we can finally reconstruct, because as I told you, city GAN will work on CSVs. So the idea is to generate the CSVs, and from the CSV the packets, and then to generate the packets to the target system. Okay, so there is of course some complexity that are specific to this protocol, but also there is some rules in the generation. For example, there is some fields that we are not relevant to change, like for example all the source IP, destination IP, ports, etc. This is something that we should not change, otherwise the packet will not even reach the target. So there is some static fields to be also taken into account. And also there is other rules that are more logic rules. So if I change something in the request, finally in the response and in the continuation of the flow, I need to use, for example, the same ID of the user in the same flow, for example, things like that are specific to some attacks. This part is more linked to this LLM-based rule generation. As I told you, we are able to, using some prompt, to generate this kind of rules. So of course, we need to, first of all, train and give the constraints related to our rule and provide some examples, etc., to be able to generate rules that have a sense. And it was successful for, let's say, when we have unique modification, only one mutation at the same time, this is always working. But where we combine a lot of mutations, it's more complex, and there is some rooms to improve this the generation of rules. We applied this to, as I told you, several kind of attacks. So this attack is more related to privacy. I have a video. I don't know if it will work. Let me check.
In this demo, we will show how Network Fuzzer can be used to perform a DICOM extraction attack, a realistic multi-phase intrusion scenario targeting medical imaging servers, such as Orthang via the DICOM protocol. The goal of this attack is to silently extract sensitive patient data and medical images. We assume that the attacker has already gained unauthorized access to the internal network. From there, the attacker can perform reconnaissance, intercept DICOM communications, and launch targeted attacks against a misconfigured server. The scenario consists of 5 main steps. The attack begins with step 1 discovery, where the attacker scans the network using tools like Nmap to identify active DICOM endpoints on port 4242. Once a server is found, the attacker proceeds to step 2, called AET brute force. In this phase, Network Fuzzer is used to send repeated A-associate RQ packets with different called AET values in an attempt to establish a valid session. After discovering a valid called AET and successfully establishing a session, the attack moves to step 3, patient metadata enumeration. Here, Network Fuzzer sends crafted cFind queries to the Orthic server to retrieve sensitive metadata, including patient names, study dates, and unique identifiers such as the study instance UID. In step 4, DICOM file extraction, the attacker uses these identifiers to send CMove requests and download DICOM images, which may then be analyzed, modified, or exfiltrated in step 5 optional analysis for malicious purposes. Here is our simulated environment for the DICOM protocol testing scenario. On the left, a client machine runs the DICOM simulation along with Network Fuzzer to generate and inject test traffic, including potential attack scenarios. On the right, a server machine host, or think, deployed as a service to process and respond to DICOM requests. Additionally, the MMT security monitoring framework is installed on the server to perform packet sniffing and traffic analysis. Using closed-loop fuzzing, Network Fuzzer dynamically adapts its inputs based on server feedback, fine-tuning its behavior through on-the-fly rule generation to gather the maximum amount of information. In step 2, it iterates over plausible called AET values by modifying normal traffic and crafting minimal, valid associate RQ packets. Each response is analyzed, and associate accept confirms a valid call AET, while a rejection or a warning in the server logs triggers further refinement. In step 3, we use a LLM-based rule generator to create a rule for modifying the patient name field in PData packets. A new rule with ID 47 is generated in XML format, compiled, and used by Network Fuzzer. Network Fuzzer then takes advantage of the DICOM cFind service by gradually fuzzing the patient name field, starting with a single question mark, then 2 question marks, and so on, to infer the length of valid names. Once the length is identified, it brute forces the initial characters and analyzes server response sizes. A 154-byte response with 100 bytes of payload indicates no match, while larger responses suggest valid entries. Eventually, a valid patient name of length 9, starting with R, is found. Using the extracted metadata from the server's responses, we proceed to retrieve the corresponding DICOM images. Thank you for your attention. In this demo.
Oops. So we saw here an example of some brute force attack that has been generated by this network fuzzer, how we are able to retrieve the information of the user and retrieve his images. So this kind of things can be used by this tool, and we are doing a lot of other kind of attacks. The evaluation is ongoing on the hospital critical infrastructure in Portugal. We need to take into account that this infrastructure is already secure, it's operational, and almost 97% of the traffic that we generate is already filtered either by the firewall or by the kernel. Meaning that they have already something that is secure enough, but all the other packets that are reaching the PAC server do not have a big impact. And we are continuing this evaluation to generate more information. That's why we are using this test beds, because in the we are using some PAC server that are open source. So this Orthic server, and we are able to inject some known vulnerabilities inside it. So at least to see how fast we can discover these issues if we do random generation or gun-based generation. And this is what we are doing now in terms of preliminary evaluation. It's also something that is ongoing, but of course, in terms of setup effort, we know that when we have some AI-based fuzzing, the setup is, let's say, more difficult than the random one. But at least the number of generated packets are high, and also their impact are higher. So we have more frequent, let's say, detection of issues. In terms of values, we have already collecting some values that will be submitted in a paper for the RS conference. So this there is a deadline for end of this month, and we are collecting this kind of information. I need to conclude because I'm already out of time. The most important thing is to know that AI is also used by attackers, not only by, let's say, a security expert, and they are also generating many kinds of let's say, attacks like AI-powered phishing emails that are more and more realistic, more the AI deepfake scams, adaptive malware. The idea is also to work on the capabilities of intrusion detection system that have this anomaly detection to know what kind of AI behind this anomaly detection to be able to evade this AI by sending some mutation of the same attack that are not detectable by the intrusion detection system. So this is something that is also very important for us as the solution provider for intrusion detection system to have also some adaptive and anomaly detectors that are always, let's say, adapting their models and improving their models. For the specific part of fuzzing, there is more improvements. If you would like to collaborate with us, the project is open source, and if this field is of interest for you, it will be very happy for us to build some collaboration and work together on such improvements. Thank you. Yep. And if you have any questions.
I know everybody.
Yes.
Yeah, sure. So can you go back a few slides? Because the big paper.
The big table.
So yeah, I'm a little bit concerned about the detection of big vulnerabilities. I understand that frequent is your goal, but in your presentation you did not really quantify it.
Yeah, this is something that we are now collecting the information. I can give you some hints about that. The idea is to limit ourselves in terms of time. So either I will write some, if it is rule-based fuzzing, to say what I can do during 2 days, okay? I will write the rules, I will generate the attacks, I will see what I can find during these 2 days. The same way in the random fuzzing, there is nothing, it's random, so we will generate a really huge thing, but we need to take into account that since it's a kind of combinatory between data and mutation function, etc., we can take a lot of time to generate things that are not impactful at all, and we will lose a lot of time. And with this AI-based fuzzer, we will be able to detect more things in the same period of time if we do it randomly.
Hopefully.
Hopefully, yes. But it depends also on the AI, how we are building things. That means if we, from the beginning, we know the vulnerabilities of the protocol. In the sense, that's why we have this LLM generation of rules. And if we have also the feedback of the server, so some of let's say some of the generation that we are doing will be from the beginning discarding. Say this kind of mutation will not work. I will not work on this kind of thing. But I agree with you that is hopefully because in some cases, and this was the case of the HES real operational system where we were not able to detect anything. It was secure enough because they have a very good firewall, very good things, and it was very difficult to find either problem.
Was it secure or was it because you were not able to generate the relevant data?
So that's why we are working on this, not fake, it's test bed, but we included some problems known in the servers, and we are able to detect them. So in terms of detection, there is a possibility. Why
automatically generate relevant patterns? And what could be the core? So, for example, you have a system with 24.
I totally agree with you. It can be the fact that we are not able to see to generate things that are relevant for an operational system. That is, of course, these kind of systems, e-health, is one of the critical infrastructure and sector that are even listed in the NIS2 directive, like energy, banking, etc., where they put a lot of effort on building a resilient system. And in general, it's very, very difficult also to break this this kind of system. But we are continuing the work because if it doesn't work, that doesn't mean that the tool is bad. Is only the way of generating can be somehow improved. I totally agree with you in this case. So it's in an operational part, and this is our target, is more difficult than do it in a fake environment or simulated environment. Agree.
Any other questions? Oh, good. Thank you.